All right, everybody, as we get later into Chapter 4 here in Algebra 2, or whatever class or whatever section you're in, this concept of simplifying radicals can become important at a lot of steps of mathematics. So I thought I'd make just a short video right here, hopefully refreshing your memory on how to do this. This is a skill that is actually taught in Algebra 1 and in geometry. However, at both of those levels, we let you guys use the TI-30XS Multiview, which does this for you. So let's go ahead and walk through it here, because ironically, as you get higher up the ladder, your TI-84 that you are using in Algebra 2 or your TI-Nspire that you might be using in pre-calc won't do this for you. The concept of simplifying radicals is a pretty simple one. Anytime you have the square root of a number that can be expressed as a product of two other numbers, a times b, that square root can be split up into the product of two individual square roots. You can break this up and make it the square root of a multiplied by the square root of b. So the square root of a product can be rewritten as the product of two individual square roots. And I'll kind of demonstrate that in the problem we're about to do next. So that's really it, although that probably doesn't mean a whole lot to you, but we're going to show you three examples here in a second that kind of ram that point home. Before we go any further, though, you are not going to be any good at all at simplifying radicals if you don't have a sense for this group of numbers right here, everybody, the numbers that are perfect squares. Now, if you have forgotten what that word means, perfect squares are numbers that have a square root that can be expressed as a rational number. So what does that mean? If you guys come across a number and try to take the square root of it and it works out nicely, that number is most likely a perfect square. But if it works out to be a bunch of gobbledygook and a big mess, like a big, messy, nasty decimal, then it's probably not a perfect square. So I'm just going to run through the list of perfect squares with you. This is not all of the perfect squares, everybody, because that set actually contains an infinite number of numbers, but we're going to run through a few of them. The first perfect square, everybody, is 0. And the reason that 0 is a perfect square is because there is a rational number times itself that equals 0. And that number is 0. So the square root of 0 is 0. There you go. 1 is a perfect square as well, because the square root of 1 is 1. Now, don't write this one down. 2 is not a perfect square. And the reason 2 is not a perfect square is there is no rational number times itself that equals 2. The square root of 2 does exist, but it's an ugly number that's about 1.414, and that's as much as I have memorized, and then it goes on and on from there. But it doesn't work out nicely, so 2 is not a perfect square. The next number that is 4, because the square root of 4 is 2. And going on from there, guys, we're going to list a few more. 9, and the next one then is 16. Now, real quick, if you notice, guys, I wouldn't write this in your notes, but the reason these numbers are perfect squares, watch what happens if I start taking the square root of each of these. Square root of 0 is 0. Square root of 1 is 1. The square root of 4 is 2. The square root of 9, is 3. The square root of 16 is 4. And now I think it's fairly obvious if you look at these numbers here what our pattern is. So as I try to keep going on my list here in red, mentally you can say, okay, that 16 there was 4 squared. So the next one is going to be the square of 5, which is 25. The next one is 6 squared, that's 36, followed by 7 squared, which is 49. 8 squared, which is 64. And as I said, this is actually an infinite set here, everybody, so there's no limit to how far we're going to go with this one here. However, all right, let's go a little bit further. 9 squared is going to be 81. 10 squared is 100. Now we're getting into triple digits. 11 squared is 121. 12 squared is 144. Now, how far you guys should go in memorizing these perfect squares? This right here is the first 13 of them. These are numbers you definitely want to know. And it certainly doesn't hurt to go a little bit further. 13 squared is 169. 14 squared is 196. 15 is 225. And most teachers would tell you that's probably far enough. Although if you really wanted to impress people and win influence over those around you guys, there you go. 16 squared is 256. 17 squared is 289. Everybody knows that. 18 squared is 324. 19 is 361. 20 is 400. And so so on and so forth, forever and ever. Amen. So anyway, guys, there's a bunch, but really, if you get to 225, you're probably in pretty good shape, and you don't need the rest of these here. So those are ones you should know. All right, so let's see this concept in action. And I'm starting you off with a pretty dumb example here, guys, because I'm asking you what the square root of 36 is, and every one of you is going to look at that and say, oh, that's a perfect square, and the answer is 6. Well, guess what? You're right, and I'm not here to tell you that the square root of 36 is not 6. But I did want to do this one with you because it illustrates the concept here that we talked about on the previous slide, that you can break a square root of a product down into the product of two square roots. You wouldn't really choose to do this problem this way, but humor me for a second, everybody. 36 could be rewritten as the product of two numbers that actually have something cool in common. They're both perfect squares. 36 can be broken down into 9 times 4. And now I can apply that property that we talked about right here, that the square root of a product can be written as the product of two different square roots. So I can now make this the square root of 9 multiplied by the square root of 4. And since both 9 and 4 are perfect squares, we can evaluate these. The square root of 9 is 3. Not the square root of 3, guys. That radical doesn't stay there. The square root of 9 is just 3. Times, and the square root of 4 is 2, and our problem is now 3 times 2, and our answer, of course, is 6. So obviously, you didn't need this trick, this method right here, for simplifying radicals on something like the square root of 36, but that little trick might come in handy, and hopefully it illustrates that this method works. Let's talk about a second example here, guys. The square root of 50. Now, unlike in the previous problem, 50 did not show up here in red in our list of perfect squares. I see that 49 is a perfect square. Its square root is 7. So I'm thinking that the square root of 50 is probably a little bit bigger than 7. But it's not 7 itself. So the square root of 50 is what we call an irrational number. It doesn't have a nice, easy way of being expressed. Even if you were to type this into your calculator, which we'll do in a minute, you end up with an ugly repeating decimal. So what we try to do then, everybody, is we try to think about that list of all of the numbers there in red, and we try to find a perfect square that divides evenly into this 50. And I'm hoping you guys have spent enough time dealing with quarters in your life to realize that 50 cents is just 2 of those quarters. The only perfect square in this list that divides evenly into 50 is that 25 right there. On the next example, I'll give you a hint for how to figure that out if it's not obvious to you, but this one probably is. So I break the 50 down into 25 times 2. Now, I use the property we discussed. I split this radical up into the square root of 25 multiplied by the square root of 2. And now, unlike the previous problem, only one of these radicands, the number underneath the radical, is a perfect square. So I can only evaluate one of them. The square root of 25 is just 5. And there is nothing we can do to simplify the square root of 2, so it just tags along as a factor being multiplied by that 5. So the square root of 50 simplifies into 5 times the square root of 2. And that, everybody, is a really typical example of what a simplification of radical problems looks like. Now, the reason that this answer is now in simple radical form is that the radicand, which is now 2, doesn't contain any perfect square factors other than 1. Initially, the radicand was 50, and that contained this factor here of 25. So that's why the original expression, the square root of 50, was not in simple radical form, but why the answer is in simple radical form. And now I just wanted to talk real quick about what it is that we've accomplished here, everybody. We've now said that the square root of 50, and I don't want to understate this, guys, the square root of 50 is equal to 5 times the square root of 2. So let me just rewrite that now. And of course, mathematically, the equal symbol is really important. It means that the left side and the right side of this equation have the exact same value. Now, it might not be obvious to you guys that the square root of 50 is the same value as 5 root 2, but who do you guys trust more than your math teachers? Your calculators, that's right. So if I were to go to Desmos right here, and I were to ask Desmos, hey Desmos, what is the square root of 50? And hit enter, it gives us this really ugly decimal here of 7.071067 blah blah blah. Now, the calculator has been programmed to only give us, what is that, guys? I think 10 decimal places after the decimal point. That's actually an infinite decimal that goes on forever and never ends and never repeats. So, have I proven anything? Probably not. But hopefully this will put your mind at ease. The answer that we came up with was 5 times the square root of 2. That's the simplified version of the square root of 50. So watch now what happens if I ask the calculator, what is 5 multiplied by, that multiplication sign actually isn't important, times the square root of 2. You'll notice, guys, it gives us the exact same decimal, again, 7.071. So really what this tells us there, guys, is that both the left side, 7.071, and the right side have the exact same decimal value. And maybe that puts your mind at ease a little bit that the square root of 50 is in fact equal to this. Okay, so that's how you would do something like the square root of 50. And I wanted to give you one more, kind of a tough one right here, the square root of 108. And let's talk about how we would do this. So we're going to try to break this up, everybody, into the product of two numbers, one of which is hopefully a perfect square. So as you go through that list here, guys, let me go back to the red numbers here. I'm going to show you first the wrong way to do this problem. The wrong way to do a problem like this is to start right, you never start with 0, but to start here with 1, you never start with 1 either, but to start small and then work your way down the list. Now, if I do it that way, the first thing I'm going to think about is 4. And so the question in my head is, does 4 go evenly into 108? So I would imagine most of us would go to our calculator now and ask it, hey, calculator, what is 108 divided by 4? And we would hope that it works out nicely. And it does. We end up with 27. So, again, this is not the way I'd recommend doing this problem, but the 108 can be split up into 4 times 27. Okay, now we break it up. That's the square root of 4 times the square root of 27, and the square root of 4 is 2. And most people are going to leave the square root of 27 there, box it up, and be done with this problem. And unfortunately, guys, you've done some nice work here, but you're not done yet. You haven't simplified this fully. This answer of 2 root 27 is not in simple radical form because if we look at the radicand, 27, there's another perfect square factor that divides evenly into that 27. Maybe you see it already. And so here's what we're going to do. Actually, this work isn't all for naught. I'm still going to come back and show you how to do this the better way. But you just keep going with this problem now. There's a 2 out in front, but now the 27 can be split up into, maybe you saw it, what perfect square goes into 27? That's 9 multiplied by 3. So now you'll make that 2 times the square root of 9 times the square root of 3, and that square root of 9 can be evaluated or simplified. This is 2 times the square root of 9 is 3. And you can't do anything with the square root of 3. And now you put the 2 and the 3 together to make 6 times the square root of 3. And that answer is in simple radical form, well, basically because 3 is prime. It doesn't have any perfect square factor that goes into it other than 1. So guys, that's how you can do this problem in 2 steps. And it's correct to do it that way, but all of us would rather get an answer in 1 step rather than 2, so let me show you the right way to do this problem. I said that the wrong way was to start here at 4 and work your way down. Okay, what we actually want to do is take the biggest bite out of this that we can. So I'm going to start not with small numbers here, but I'm going to start with big numbers. Now let's go back and let's talk about a basic piece of number theory. If I were to ask you guys, what is the largest number that divides into 108? The answer to that is 108. Okay, so in general, the largest number that divides into any number is the number itself. Well, obviously, 108 is not a perfect square. It doesn't show up in this chart. So now here's my next question for you guys. If 108 doesn't work, what is the second largest number that goes into 108? And the answer to that, everybody, some of you probably just came up with it, is 54. And if you're not sure where that came from, if you take 108 and divide it by 2, cut it in half, that gets you this number right here. So let's recap. The biggest number that goes into 108 is 108. The second biggest number that goes into 108 is 54. Now, what's the significance of that? If I were to look at this list, I don't have to even think about any number here that's bigger than 54. So I could kind of draw a line right here, and don't do this in your notes, but there is no way that 64 divides evenly into 108 because it's bigger than half of that number. Likewise, neither does 81, 100, none of these numbers here have a chance of dividing into 108. 49 is where I need to start thinking. So 49, that's the number I want to know here. Does that divide evenly into 108? Let's find out. Divided by 49, and we end up with this ugly decimal. So 49 didn't work. So back to the drawing board here. Nope, not 49. The next number we should think about is 36. So let's give that one a try. 108, nope, I forgot the 0 there. 108, got it. Divided by 30, okay. 108 is a big number. It's not one that was in your multiplication table back in 3rd or 4th grade when you learned it. So I wouldn't be surprised if anybody at this level didn't realize that 36 goes evenly into 108, but this is how we test it. This is how we find that biggest perfect square. So right here on line 5 of my calculator, I have learned something I didn't know. 108 divided by 36 is 3. So what I really should have done, guys, on this problem is split that 108 up right off the bat into 36 times 3. You want to pull the biggest perfect square out that you can, not the smallest. So I split that up now, the square root of 36 times the square root of 3, and the square root of 36 evaluates to a 6, and the root 3 just tags along for the ride. And that, everybody, is the quick and direct way that you are able to simplify radicals. And again, if I wanted to make sure that I was right on my TI-84, I'd probably type in the original problem, which was the square root of 108, and sure enough, I get this ugly decimal. And then I'd probably type in my answer, what I think is the answer, 6 times the square root of 3, and you just want to make sure you get the same decimal numerical value for both the original problem here in line 6 and also then my answer, which is in line 7. So at this point, everybody, I feel pretty good that I got this answer right, and that's 6 root 3. Okay, all right. Later on this year, in fact, in Chapter 5 in Algebra 2, we learn how to do this with things like cube roots, and we learn how to do it with variables and exponents, but I think I'll save that for another video. All right, everybody, so hopefully that refreshes your memory a little bit on how to simplify radicals, and that'll help you here moving forward.